Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Misalignment. Misalignment can occur in several places in rotating machinery. For example, misalignment can occur along the shaft centerline between bearings. Misalignment can also occur in meshing gears. However, misalignment more frequently occurs when two machines are coupled together. When misalignment occurs, the first three harmonics are generated. If coupling halves are misaligned, the first three harmonics of rotating speed are generated. If gears are misaligned, the first three harmonics of gear mesh frequency can be generated. For these reasons, solo data should be taken on all motors and turbines before they are coupled to the driven unit. If you want to know the type of misalignment, take data in the horizontal, vertical, and axial directions on the drive and off ends of the drive and driven units. If the first three harmonics are distinctive in 1. The horizontal direction, there is vertical offset misalignment. 2. The vertical direction, there is horizontal offset misalignment. 3. The axial direction, there is angular misalignment. And 4. All directions, there are horizontal offset, vertical offset, and angular misalignment. If the first three harmonics are distinctive, then misalignment is present, regardless of the amplitude within prescribed calibration levels. The problem is that most people think low amplitude levels indicate a good machine. This could be true in some situations, however, there are severe problems that can occur with low amplitudes. Misalignment is one of them. In the real world, most misalignment problems go undetected and unrepaired until the coupling, shaft fits, or the bearings are worn out. There are many types, combinations, and degrees of misalignment. The signals obtained can also vary with coupling type, shaft size, and speed. Because of these factors, a single example of misalignment is not adequate. However, this writer has observed several distinctive patterns associated with misalignment. Please remember various combinations of amplitude and phase can cause some signals to be very different. Figure 6 contains a spectrum and time signal of misalignment. Please note. Number 1, the first three harmonics of speed are distinctive. The amplitude relationships could vary significantly. If the amplitude of the second harmonic is higher than the first and third harmonics, the shaft may be bent. Number 2, the time signal contains a fast rise time on one side and two positive going peaks on the other side of each cycle. As the shafts rotate, the coupling bends and then frees up once each revolution. When the coupling is binding, the three peaks are generated. When the coupling frees up, the fast rise time is generated. Number 3, the time signal is normally truncated on the negative side because the signals are in phase. However, in some cases, the signals could be out of phase. Operating speeds above first critical is a good example. And number 4, the time period for each half revolution may not be equal. The unit speed decreases when the coupling is in a bind and increases when the coupling is free. The amplitudes of the first three harmonics can approach a 6 dB per octave slope, as in Figure 7, or a 12 dB per octave slope, as in Figure 8. The 6 dB per octave slope indicates a level of increased binding of the coupling. When the signals approach a 12 dB per octave slope, the amplitude may increase, the coupling may be locked and rigid, and severe wear and/or failure may occur relatively quickly. Thank you.